Okay, we're on. First of all, are there any questions? Now, I'm doing things a little bit differently from the way I usually do them because I'm trying to compress things. And so I'm not sure if it's really making sense. And the only way I know that is if you tell me it's not making sense and ask me questions. So I assume that it is making sense? Okay. So we were talking about the Poisson process. So I want to, my objective here is to get to the point where you can, where homework number 1, which was given for the last course and which I passed out but said that you didn't have to turn in, where that makes sense to you so you can do it. And then I'm going to assign a homework 2, which is similar to that. All right, so we were talking about the Poisson process. And the idea there is that we have this process in which events, we'll view them as arrivals, but they don't have to be, occur randomly in time. And by randomly, what we mean is that we made a model in which we imagine that each point on the line is as likely to have an event as every other point. So what we did was we broke this down into an interval 0t, and then we made little tiny intervals, and then we made some assumptions. In particular, we said that in each interval you can have at most one arrival. Either there is an arrival or there isn't an arrival. All intervals are of equal length and so have equal probability of having an arrival. And whether or not there's an arrival in any interval is independent of every other interval. So that means that we have independent intervals. And then what we did is we, based on that, we made a limiting argument. We calculated the probability that x, which by definition is the time until the first arrival. Now here, that would be the x. We calculated the probability that x, the time until the first arrival, was greater than t for any t. And we showed that if you wrote such an expression and then took the limit as the number of intervals goes to infinity, meaning that the width of each interval goes to 0, so the intervals shrink to points, then the probability that x is greater than t is e to the minus lambda t, where lambda is the arrival rate. Which means that the distribution function of x evaluated at t, which by definition is the probability that x is less than or equal to t, is 1 minus e to the minus lambda t for t greater than or equal to 0. Now, then we looked at some properties of this process. This is called a Poisson process if we imagine that we have a sequence of these x's. So here's x1, x2 would be the time until the next arrival, x3 would be the time until the next arrival, and so forth. So if I have this sequence of x's, which are independent and identically distributed, and their distribution function is the exponential, then this is said to be a Poisson process. And obviously, a Poisson process is the simplest, non-trivial description of events occurring randomly in time. And this is the process. This is what we're going to use ordinarily as a description of arrivals in our queuing model. Now, some of the properties of Poisson process. The one that we discussed last time was that it's memoryless. And the fact that it's memoryless, well, that's just a statement of conditional probability. But in essence, it follows from our original model, which said that what happens in any little interval is independent of every other interval. So if it's independent, what that means is that the probability is not affected by what happens, which means that it has no memory. So it's not surprising then that this memoryless property would persist. Now, another property of interest is that suppose I ask for, and now I'm looking in the book on page 44. So I'm kind of skipping around back and forth in the book. I'll try and tell you where I am if I know where I am. So on the bottom of page 44, there's a statement goes something like this. What's the probability that x lies in this interval between t and t plus h, given that x is greater than t? So here is 0, here's t plus h. So h is going to be a small interval. That's what I mean by that. And I know that x is at least t, so I want to know the probability that it will, that if it has lasted at least t, it's going to end between t and t plus h. Now, first thing we know is that the value of t is irrelevant by the memoryless or Markov property, because it doesn't make any difference how much time has elapsed since the last arrival. The distribution of time until the next arrival is still the same and still exponential. So that means that, this probability would be given by 1 minus e to the minus lambda h. Okay, that's this statement right here. That's the probability that starting here, the time until the next arrival is less than a time interval of length h. Now remember that h is small. What I'm going to do is I'm going to expand the exponential. So I'm going to write this as 1 minus, and then the exponential becomes 1 minus lambda h plus lambda h squared over factorial 2 minus lambda h cubed over factorial 3 plus minus and so on. So this is just the Maclaurin series expansion of e to the minus lambda h. And then I rewrite that. What I'm going to do is I'll cancel the 1. The first term here becomes lambda h. And everything else looks like a term with h in it that's either squared or cubed or higher. So what I'm going to do is I'm going to call all that other stuff O of h. And what O of h means is O of h is equal to, in a sense, what that means is, I should write it this way. Anything that's said to be O of h, little o of h, has the property that if I divided it by h and then let h go to 0, I get 0. That's a definition. Okay, that's obviously true here because all of the terms that I have left over have h squared, h cubed, or something higher in there. So if I divide by h, I still have at least a power of h in the numerator. As I let h go to 0, the whole thing goes to 0. So in effect, this term is something that goes to 0 very fast as h goes to 0, as the interval shrinks to a point. So what this says, in effect, is that if I have a little tiny interval of length h, as h goes to 0, the probability that I will have an arrow, an event, occur in that interval is proportional to h. And the proportionality constant is the arrival rate. And the rest of it is stuff that I can ignore because it goes to 0 very quickly. So I want to use, this is one of the facts that I want to remember about a Poisson process. In effect, it says that every little interval, no matter where it's located, if the interval is small enough, then the probability of having an arrival during that interval is proportional to the length of the interval in the limit as the length of the interval goes to 0. The proportionality constant is the arrival rate. And that we're deriving this for a Poisson process, but actually this characterizes a Poisson process. I assumed it was a Poisson process, and I showed that it's true. But if I started from here, then I could also find that I would have exponential inter-arrival times, which means a Poisson process. And this is done in the book. Okay, so this is one of the facts that I want to remember. Okay, another fact. Suppose that x1, x2, xn are IID exponential. In other words, suppose I have a sequence of independent random variables, all of which have the same exponential distribution. And what I would like to do is I'd like to say something about the min. That is, what I want to ask is this. What's the probability that the smallest of all of these exponential variables is greater than t? What's the probability the minimum is greater than t? And now I say, well, let's see. If the min is greater than t, that means that they are all greater than t. So that means that x1 must be greater than t, and x2 must be greater than t, and so on, up through xn. They must all be greater than t. But since they're independent, that means that the product, the joint probability, is the product of the marginal probabilities. So that means I have here the probability that x1 is greater than t times the probability that x2 is greater than t, and so on, times the probability that xn is greater than t. Now, if they are exponential, they don't even have to be identical, but I'm assuming them for this case. But even if they weren't, this would be true. This would be e to the minus lambda 1, let's say, t. Except if they're identical, they all have the same lambda. I'll write it out. Let's assume that they're not identical. Okay, so let's just assume that they're independent. We'll get rid of that. We'll assume they're independent random variables, but not exponential, but not necessarily identical. So they can have different lambdas. So this probability is e to the minus lambda 1t. The next one is e to the minus lambda 2t, and so forth, e to the minus lambda nt. And then, of course, by the property of exponentials, those exponents add. So I can write that as e to the minus lambda 1 plus lambda 2, and so forth, plus lambda nt. And then what you see is that the probability that the min is greater than t is given by e to the minus something t, where the something is the sum of the rates. And so therefore, the min is also exponential, because of the form e to the minus something t. So if the x's are exponential, then their minimum is also exponential, but its rate is the sum of the original rates. Of course, if the random variables are identical, then the sum of the lambdas is simply n times the common lambda, and so I get a simpler result. Okay, so if I have exponential variables expiring, so to speak, in parallel, then the time until the shortest one expires is exponentially distributed with a parameter equal to the sum of the parameters of the random variables that were in progress. Now this is in the book also, and this is on page 48. Okay, so again, I keep on stressing this. I'm assuming that you've seen this or something like it somewhere before, because I'm just reviewing this. I'm just stating all of these facts rather than going through them in a very systematic way. But I want to use these facts shortly. Now, another question has to do with, and there are a lot of more facts, but I'm just going to state the facts when I need them. I said that a process in which the x's, x1, x2, and so forth, I said that if the x's are IID exponential, then we have what's called a Poisson process. Now, you're all familiar with the Poisson distribution. And the reason that it's called the Poisson process is because suppose that I fix some interval of length t. Then the probability that during this interval of length t, I have exactly j arrivals is given by lambda t to the j over j factorial e to the minus lambda t. This, of course, is the Poisson distribution, or the Poisson probabilities. So what I'm saying, I'm going to prove it in a minute, is that if I have the x's, okay, if x1, x2 are IID exponential, then that implies this statement right here. What this means is, if the x's are exponential, that is, the times between these events have the exponential distribution function, the x's are continuous random variables, then if I fix any time interval t and ask for the distribution of the number of events that occur during that time, that number, that j, has the Poisson distribution. So this is a discrete distribution. This says that if I tell you how much time there is between events, then that implies how many events will occur in a fixed time. That's sort of common sense, but what this says is that in particular, if the times between events are exponential, then the number of events that occurs in a fixed time has the Poisson distribution. Now, the converse is also true. If I told you that for any interval, if it were true for every non-overlapping interval, that if the interval is of length t, the probability that exactly j arrivals occur is given by this expression, then it must be true that the times between those arrivals must be IID exponential, of course with the same parameter lambda. So it works both ways. And in a sense, this is not surprising, because how did we derive the exponential distribution? We derived it by saying, well, we're going to take time, and we're going to divide it up into little intervals, and we'll say that in every interval, either we have an arrival or we don't. And then we took a limit. So suppose instead of asking for how much time elapses until the next arrival, I ask for how many arrivals occur in a fixed time. Well, if I have n intervals making up my fixed time, and there's a probability p of an arrival in one of those little intervals and a probability q of no arrival, and that's all that can happen, and the intervals are independent of each other, then as everybody knows, the probability that I would have exactly j arrivals would be given by the binomial n things taken j at a time, p to the j, 1 minus p to the n minus j. This would be the probability that in these n intervals, if p is the probability of having an arrival and the intervals are independent, that exactly j intervals would have arrivals and n minus j intervals would not have arrivals. And then if I took the limit of this is just mathematics now, and I let n go to infinity, which means that this is over a fixed time, okay, so this is going to be an interval of length t. If I let n go to infinity so that the width of each interval goes to 0, so therefore I let p go to 0, in such a way that np, which is the expected value of the binomial, is equal to lambda t, some arrival rate times the length of the interval, then the answer that I'm going to get, if I actually did the mathematics, would be exactly that. So that proves, that's one way of looking at it. I'm going to give another one in a moment. That's the limiting argument that proves that if I made the same argument by which I derived the exponential, except that instead of couching it in terms of time between arrivals, I couched it in terms of number of arrivals in a fixed time, but starting from the same assumptions, then I would get the Poisson distribution for the number of arrivals in a fixed time, as opposed to earlier when I got the exponential distribution for the length of time separating the successive arrivals. Now, another nice way to do it is given by exercise 17 on page 51 and 52. Okay, so here's exercise 17. Exercise 17 says, suppose that we have a so-called renewal process meaning that we have these arrows generated by these x's, where the x's are independent and identically distributed. Now, if particular, if they also happen to be exponentially distributed, then it's a Poisson process. So what I want to do is I want to calculate the probability that in an interval of length t, I have exactly j arrivals. And now I'll do it this way. I'll say, well, let's see. The way I'll do it is I'll say, first of all, okay, let's call this 0, and let's call this t. Now, how can I have j arrivals between 0 and t? Well, first of all, the first arrival must occur someplace. So I will calculate the probability that the first arrival, let's see, I'll write it like this. Here's the probability that the first arrival occurs at time u. Okay, so there's u right there. And then I'll multiply that by the probability that during the remaining interval, whose length is t minus u, I have exactly j minus 1 additional arrivals. And then I will add that up over all possible values of u as u varies from 0 to t. Now, this is a physical argument at the moment, because first of all, it doesn't mean anything, because the probability that x, which is the time until the first arrival occurs, takes a particular value u is 0, because it's a continuous process. Okay, but now I can rewrite this, and I can say, well, let's be more precise about this. The probability that I have exactly j arrivals in an interval of length t is given by, now this part here would be the density function of the inter-arrival time evaluated at u times du. Or, to use the notation that I introduced last time, it would be the differential of the distribution function of x evaluated at u. Now, I didn't write the x1 here because, by assumption, all the x's have the same distribution function. So it doesn't matter whether it's x1, x2, whatever I call it. This just says this is interpreted as the probability that an interval drawn from this distribution will have a value that's approximately equal to u, or lies between u and u plus du. Okay, then I multiply that by the probability that in the remaining interval, whose length is t minus u, I have exactly j minus 1 arrivals. And then I sum, which in this case means integrate, as u varies from 0 to t. And so what I have is a relationship then that tells me, if you tell me what the distribution function is of the x, then I can put this then, and if I know what P0 is, if I have a starting point, then I can find P1. But if I can find P1, I can put it in here and I can find P2, and then I can find P3 and so forth. So all I need to know is what P0 is. Okay, but obviously P0 of t, well, what does that mean? That's the probability that there is no arrival in an interval of length t, any t, of course. So here's my 0, here's my t. I want the probability of no arrival in this interval if I have such a process. And if f of x is the distribution function, then this is the probability, fx of t is the probability then that the time until the first arrival is less than t. So if I want no arrivals, I want the time until the first arrival to be greater than t. So I subtract from 1. Okay, so this statement says that for every t, the probability that I have no arrival in the interval from 0 to t is equal to 1 minus the probability that the length of the interval until the next arrival is less than or equal to t. because if 1 minus that is the probability that's greater than t, and if it's greater than t, then I have no arrival. So I know what p0 is, so I can take that p0 and I can plug it into here. Excuse me, let me say again. Suppose I want to calculate p1. I know what p0 is, so when I set j equal to 1, this is p0, so I can plug that into here. I know what this is by assumption. This is the distribution function of the times between arrivals, and so this gives me p1. But once I know p1, I can take the p1, plug it into here, and I can evaluate the integral, and that's going to give me p2. And if I know the p2, I can put it into here and so forth. And in fact, if I see a pattern, then I can prove by induction that the formula that follows that pattern is a solution. Now, once you have done this, it's easy now to show that if the distribution function of the inner arrival times is the exponential, then pj of t, which satisfies this equation, is the Poisson. And in fact, that's what the exercise asks you to do. And the solution is in the solutions manual. But it's no big deal. All the insight is here and here. And everything else is just arithmetic. Once I do that, it's easy. In fact, what you can do is you can take the particular case of the exponential, put it in here, and put in the Poisson, and you'll see that when you evaluate this integral, you get exactly the same Poisson back, except that the j has gone up by 1 unit. So the key to everything is the reasoning that's right here. And the reasoning here, which works, of course, for any renewal process, I'm just specializing it here for the Poisson process, says that the probability that in an interval of length t I have j arrivals is, first of all, the probability that the first arrival occurs at time u times the probability that in the remaining interval of length t minus u, I have exactly j minus 1 other arrivals, and then I add that up as the u value right here ranges from 0 to t, covers all possibilities. Then I get my starting point, my p0, by saying, well, the probability that there is no arrival in t is the probability that the inter-arrival time is greater than t, which is 1 minus its distribution function. And that's it. That then would work for any x's. But in particular, if the x's happen to be exponential, then the Poisson probability comes out. So this proves that if I have a process in which the arrivals are generated by independent, identical intervals, and those intervals are exponential, then, okay, if the x's are IID exponential, then the probability that I will have exactly j of them in an interval of length t is given by the Poisson distribution. Okay, now suppose you wanted to go backwards. Suppose I knew that this were true. How could I get that? This is actually easier because all I say is, well, let's see. To calculate the distribution function of the time until the first interval, that's just the same thing as saying that in an interval of length t, I must have no arrivals, and that must be 1 minus the distribution function. So if I plug in 0 for j, then I will get e to the minus lambda t. Of course, 1 minus that is the exponential. And then you argue that, well, that works for every interval, and the intervals are independent of each other, and so you get the IID exponential inter-arrival times. So if we have this simple model in which we say that every point is as likely as every other point to have an arrival, and the points are independent of each other, then that implies that the times between arrivals are independent, identical, exponentially distributed. It implies that the number of arrivals in a fixed time is the Poisson distribution. The name of that is the Poisson process, and it also means that the process is memoryless. And further on, Further, it means that the probability of having an arrival in any interval of length h, no matter where that interval is located, is approximately the parameter value, the arrival rate, times the length of the interval. And then there's this other stuff, which for all practical purposes goes away. So this is the key right here. That goes away. That is, as h goes to 0, as we shrink from an interval to a point. In effect, we can ignore this. And so to a first order approximation, the probability of an arrival in a little interval is proportional to the length of the interval. So these are all properties of the Poisson process. Okay? This stuff is all in the book, too, in the section on the exponential distribution and the Poisson distribution, as well as some other stuff. Okay, now let me go back to the simulation question, and then I'll get back to this again. Any questions about this so far? Everybody see how this is going to fit together? Okay, everything I say can be supported mathematically, although I'm not being careful in the mathematical arguments. But this is not a mathematics course, and that's really not important as long as it's simple. So it's a strategy that's most important here. It's the understanding of the physics of the thing. When you actually do the arithmetic, it's easy. Yes?
The definition of P x1 equal to u means the first arrival is at exactly time equal to u.
This thing right here is what you're asking? Okay, this says, I've got this process. Here is t. I want to know the probability that between 0 and t, in this interval of length t, I have exactly j arrivals. So I say, well, let's see. First of all, if there's to be exactly j, then there's got to be a first one if j is greater than 0. Okay, so the first one must occur at some time. Let's call it u. All right, so here is time u.
Between 0 and u, right?
Well, no, this is going to be the probability that occurs exactly at u. Or, of course, that probability is 0.
Yes.
Right. So what I'm really saying is, what's the probability that occurs in a little infinitesimal interval about u, or between u and u plus du? Now, if there were a density function, I would write that as the density function of x evaluated at u du. That's what density function means. Except that I don't even require that I have a density function, because suppose the process were discrete, this still would be correct if I interpreted it correctly. So later on in the course, when we discuss Riemann-Stieltjes integration, I'm going to explain what this notation means. But for now, this is just shorthand. So whenever I write differential of distribution function, what I mean, if it exists, is density function times the differential. So in fact, if this capital F were differentiable and I took its differential, then I would get its derivative times du. The du's cancel, so to speak, and I'm back where I started. So you should interpret this for the moment. When you see this, this means this. Okay, but if that presumes that the density function exists, which means that this big F is differentiable. And what I'm saying is, even if it isn't, this still makes sense, except that it has to be evaluated a different way. But let's not worry about that for now. For now, let's just always take this to mean that. Okay, so now going back to here, what this thing says is that this piece is the probability that my first arrival occurs between u and u plus du in this infinitesimal interval. And then I multiply that by the probability that in the remaining interval, whose length is t minus u, I have exactly j minus 1 additional arrivals. And then I add those up, I sum those probabilities as the u varies from 0 up to t. That's the integral. Okay? And this kind of reasoning goes on all the time in this sort of mathematics. Well, it is recursive, but that's not that's maybe part of the point. But the other point is that I am representing things by looking at the probability that something happens in some little interval and then multiplying that by the probability that something else happens in some further interval and so on. So it's this integral and the d. That's the this is actually the theorem of total probability. These are like this is like conditional probability in a sense, in which I sum conditional probabilities, except that when you learn it in an undergraduate course, it's always discrete. It's always like this, sums. But in this application, the random variables involved are not necessarily discrete. In fact, in general, they're not. So you have to be able to make the mental shift from probabilities to density functions, or differentials to distribution functions, and from sums to integrals. Okay? Okay, so now let's get back to the simulation. And in the simulation, there were two instructions that you have to fill in. Instruction 140. And 140 says IA equals, and IA stands for inter-arrival time, and then there's instruction 200, which is X equals. Don't want to put that 1 there. And you're supposed to fill these things in. And the idea behind this is that you're imagining that you have this experiment in which you have these urns with tickets. And one urn contains these tickets in which the numbers on the tickets are the inter-arrival times, and the other urn contains the tickets, and the numbers on the tickets are the service times. In the simulation, I've used IA to represent inter-arrival times and X to represent service times. And what you do in the simulation is you imagine that you have this bunch of servers like that, and then you reach into here's time 0, you reach into this urn and you pull out an inter-arrival time, and you make that you make the number on that ticket the time at which the first arrival occurs. And then you look for a trunk, a server, and you have, in memory, you have the state of each of these servers. The state tells you when the server is next available for service. So I look at server number 1, and if the state is such that that server is available, then I reach into this urn, and I pull out a ticket, and I look at its number. That's going to be the service time. And then I make that server busy for that length of time. And then I go to this urn, and I pull out the next inter-arrival time, and I add it to the old inter-arrival time. So maybe it comes out to be here. And then this represents the arrival time of the second call. And then I want to find the trunk for it. So I look at trunk number 1 according to this diagram. Trunk number 1 is busy, so then I would look at trunk number 2. Trunk number 2 is available, so I'm going to carry the second call on the second trunk, and I find out the length of that call by now sampling again from urn number 2. And I read whatever number's on that ticket, and I make that trunk busy for that length of time. And then I generate the time for the next call. Maybe it'll occur here, and in that case it would be carried on trunk number 1 again, and so on. And so I generate this diagram, and then from this diagram, when I get done, I can calculate the fraction of calls that overflow, and I can calculate the fraction of time all the servers are simultaneously busy, and those are the performance measures that I want to compare. So in order to, now I've already gone through the logic of the simulation, and that's all straightforward. So the only thing that relates to probability in this case has to do with how I generate the numbers that are here and the numbers that are here. Okay, so now I want to give you the instructions that are going to generate this and this. Now, in order to do that, let me review what we did last time about I gave you 3 different distribution functions as examples, and I'll draw pictures of them. One of them was uniform. So we say that x, a random variable, not necessarily the service time. So now I'm just talking about generic x. We say that x is distributed as a uniform variable between 0 and 1 if its distribution function is of this form. The distribution function is given by three pieces. It's 0 if t is negative. It's t if t lies between 0 and 1. And it's 1 if t is greater than 1. And we derived this from a model. The model being, a question there? Okay, we derived this from a model, the model being that we had an interval, 0 to 1, and we're going to pick out points on this interval, and all points are equally likely. Of course, there's an infinite number of such points, but if we take the proper limiting argument, then that's what you get. And in fact, you could draw the picture of that distribution function. It's going to look like this. There's t, 0, 1, 1. There's the distribution function. It's 0 for t negative. Then it's t for t lying between 0 and 1. And then it's 1 for t greater than 1. So that's the uniform. Second one we looked at was the exponential. We said x is exponential with parameter lambda. Okay, what that means is that its distribution function is given by 0 for t negative and 1 minus e to the minus lambda t for t not negative. And of course, we derived this one from a model. There the model was that we were going to have events occurring randomly in time, and each little interval was as likely to contain an event as each other interval, and the intervals were independent of each other. Okay, so this is the one that generates the Poisson process. And then finally, we took the case where x is equal to a constant. And in that case, let me draw the picture of this, by the way. This thing, its distribution function will look something like that, where that's the value 1. That's the graph of this thing. And now suppose that the random variable always takes the same value. How could I write it in this format? And the answer is, well, all that means is that if this is the distribution function, then here is the value c, here's the value t, here's the value 1. So the distribution function must look like this. It must be 0. I'll write it here. Let's see, I'm running out of space. Okay, so the distribution function, that's this case, is equal to 0 if t is less than this constant, and then as t crosses this value right here, this constant value, then the distribution function takes the value 1. It's 1 if t is greater than or equal to c. So what it says is that for every t less than c, the probability that the random variable is less than or equal to that is 0, because it's never less than or equal to that. And for every t greater than or equal to c, the probability the random variable is less than or equal to that is 1, because it's always 1, because it always takes the value c. So here are 3 different distribution functions that we're going to be interested in. Okay, now let's talk about how we're going to generate random variable values that are described or follow those distributions, or any others for that matter. And the answer is what's called the inverse transform method. So we'll have inverse. This is one way of doing it. Inverse. This is also in the book, except it's in chapter 6. If you look it up in the index, you'll find it. It also tends to be in books on simulation, although surprisingly it's not in as many elementary books as it ought to be. It ought to be in every one of them. Okay, now the idea of the inverse transform method is that what you do is, suppose that I, for the sake of example, I have to pick some example, so I'm going to pick the exponential. I'll pick a picture that looks like an exponential. Suppose that I wanted to generate random variable values whose distribution function happened to look like that, which is what an exponential looks like. That's the value 1. Remember, a distribution function has the property that it always lies between 0 and 1, and it never decreases. Okay, so what the inverse transform method says is that, first of all, you ask the computer to generate for you a random number, which I'll call R. You take the random number, which always lies between 0 and 1, you put it on the vertical axis. You project over to the curve and down, and you call the result x. And the inverse transform method says that if R is uniform, 0, 1, then x will be distributed as whatever the formula is for that curve, which I'll call capital F. Okay? Then x is distributed as f of t. Okay, so this is very, very practical. What this says is, suppose that somehow or other I can get numbers that are uniform between 0 and 1. I can take those numbers and I can use them to generate other numbers whose distribution function is anything I want it to be, whatever I choose to be the equation of that curve. In particular, if I choose the equation of that curve to be 1 minus e to the minus lambda t, then the x's will be exponential. If I choose this to be something else, then the x's will be that something else. Now, the reason that this works so nicely is that the computer ordinarily has built into it a routine by which it generates these r's. It's generated by what's called the random number generator, or pseudo-random number generator. Okay, so I'll write pseudo, P-S-E-U-D-O, random number generator. Pseudo means false. And the reason for that is that the computer has an algorithm in it by which it generates numbers that appear to be random, randomly lie between 0 and 1. In other words, they appear to be uniform between 0 and 1. But actually, they're deterministic. They're not random. So that if I were to see a sequence of these numbers and I didn't recognize them, and then I performed tests of randomness on those numbers, they would look to me like they came from a uniform distribution. But if I recognized where they came from, recognized the formula by which they were generated, then I could predict exactly what everything was going to give me in the future. For example, here's a way that I could generate random numbers, although it's not practical, but as an illustration shows what's going on. Suppose that I had an algorithm that generates pi to any degree of accuracy I want. So it could generate 3.14159 and so on forever. And these numbers, no large sequence. That is, there's no, I'm not sure how to say it right. There's no apparent pattern here. There's no period such that after a finite number of digits, then everything repeats itself. So I could take this as a random number generator. What I could do is I could say, all right, I'm going to generate this, and what I'll do is I'll have some starting point. That's called the seed. So someplace I start, and let's say that at this starting point the numbers are 5, 5, 6, 1, 9, 2, 3, 5, 9, 8, something like that. Then what I could do is I'll say, all right, if I want my random number generator to generate numbers to 2 decimal places, I'll take my first random number to be 0.55 and my second one to be 0.61, and my third one to be 0.92, and so forth. Now, if the digits from pi appear to be random, if you didn't know they were from pi, then what you would see is, well, each digit would appear approximately 1/10 of the time, and they appear to be independent of each other. So what I would be generating would be, I would be generating uniform variables, numbers that are uniformly distributed between 0 and 1 to 2 decimal places. So this might very well pass tests of randomness and independence. And so if I saw the string, I couldn't predict what's happening. But if I suddenly said, wait a minute, this is the expansion of pi starting at the 328th digit, if I could say that, then it's no longer random because I could predict exactly what's going on. Okay, so what the computer does is it generates a sequence, a string of numbers by a deterministic algorithm. Not this algorithm, but some algorithm. Doesn't make any difference from our purposes. All that matters is that it does it quickly and that the numbers that it does will pass tests of statistical randomness and appear to be uniformly distributed. So the computer generates the R's for you. We assume that they are in fact uniform. And now what I want to do is show that if the R's are uniform, then the X's will have as their distribution function whatever this formula here happens to be. Okay? Okay, so let me do it like this. Let's see. I'm going to change this to call this U. I think that makes it easier to understand. So there's a U, and there's a U. And now what I'll do is I want to calculate the probability. Let's see. Let me erase this. This is one of these proofs that is quicker than the eye. It's so simple that it's confusing. What I want to calculate is the probability that the X so calculated will be less than or equal to t. So imagine then that, say, here is value t. So if the X is to be less than or equal to the t, then obviously the R must be less than or equal to f of t. So that's the same thing as the probability that R is less than or equal to f of t. But R is uniformly distributed. So the probability that R is less than or equal to f of t is f of t. Right? Here's the distribution function of a random variable x that's uniform 0, 1. The probability that's less than or equal to t is t, as long as the value lies between 0 and 1. Okay? So if the R is uniform between 0 and 1, then the probability that it's less than f of t is equal to the ratio of that interval, whose width is f of t, to that interval, whose width is 1. So in other words, the answer is f of t. So if the probability that x is less than or equal to t is f of t, by definition, that is the distribution function of x. That's what the distribution function of x is. It's the probability that x is less than or equal to t. So therefore, by this argument, the distribution function of x is whatever this curve happens to be. So if I want to generate values that are exponentially distributed, then all I do is set this curve equal to an exponential. Okay? So suppose I want my inter-arrival times to be exponential, or my x to be exponential. Let's call it x for the moment, since that's what I have here. Suppose I want to generate x's that are exponential. So that means that, suppose that capital F is given by the formula 1 minus e to the minus lambda u. Okay, so what that means is that the relationship between my x and my r is this. It is that that r, the random value, is equal to 1 minus e to the minus lambda x. That's the relationship between r and x if this curve has this formula, which is the same thing as saying that e to the minus lambda x is equal to 1 minus r, which is the same thing as saying that that minus lambda x is equal to the logarithm, the natural logarithm of 1 minus r, which is the same thing as saying that x is equal to minus 1 over lambda times the natural log of 1 minus r. So this is supposed to be, yeah, this is x. That's lambda. I'll get those confused. In code, if I were writing this in BASIC, then I would say that x equals minus ln, well, in BASIC, anyhow, natural log is, in my BASIC, is log. Then here, I have to write 1 minus the random number. In my BASIC, the way I generate a random number is I write rnd1, although it may be different in your particular system, whatever it may be. And then I have to divide by lambda, which my BASIC doesn't have a lambda, doesn't take Greek letters, so I'll call it L. So I would be dividing by L. So this instruction then would say, every time I execute this instruction, it would say, generate a random number, subtract it from 1, take its logarithm. That's going to be a negative number, of course. Multiplying it by a minus sign makes it positive. That would give me an exponential value whose rate is 1, and this L is just a scale factor that adjusts it. So if I said now that I want to generate inter-arrival times that are exponentially distributed with any specific numerical rate, then I would just write IA equals minus the log of 1 minus a random number divided by that rate, or multiplied by the reciprocal of that rate, which is the inter-arrival times. So that instruction would do it. OK? So that's all there is to it. Suppose I wanted to generate, OK, so if I want to generate exponential inter-arrival times, that is, if I want to generate Poisson process or Poisson arrivals, then this instruction would read x equals minus the log of 1 minus a random number divided by the arrival rate or multiplied by the inter-arrival time, whatever that might be. Let's see, the way the problem is written is it says, in each case, make the arrival rate to be 4. Okay, so if the arrival rate is 4, that means lambda is 4. So the inter-arrival time would be 1/4, and that would be 0.25. So the easiest way to do this would be to write it as minus 0.25 times the log of 1 minus the random number. And in fact, I'll leave it as an exercise, unless you want me to do it. It's sort of obvious that if I have a random number, that is, if this piece here is uniform between 0 and 1, then when I subtract from 1, the result is also uniform between 0 and 1. All it does is shift things over in the following, reflect in the following way. Here's 0, here's 1. If here's my random number, then 1 minus the random number just shifts it, just takes this value and shifts it over here. So it just reflects it about the middle. So what that means is that I could actually make my program run faster by writing log of a random number instead of log of 1 minus a random number. The numbers would be different, but the distribution would be the same. I would be saving myself this subtraction every time I did it. So that makes it faster, but a little bit less transparent. OK, so this instruction will generate exponential inter-arrival times with rate 4. So this generates a Poisson process with calls arriving at the rate of 4 calls per unit time. Now suppose I wanted to generate exponential service times. Okay, problem number 1, case 1 says, do it for Poisson arrivals and exponential service times. If I wanted exponential service times, then I would write minus log of 1 minus a random number, because I have to generate a new random number. I can't use the same random number for both, or the service times and the inter-arrival times would not be independent. And then I would multiply by the average service time, whatever that may be, which according to this is 2.4. Okay, so for case number 1, this would be x equals minus 2.4 times the log of 1 minus a random number. Every time it sees this instruction, it generates the next random number in the sequence. Okay, so this would give me the first case in that homework assignment. Suppose I wanted the service times to be constant, as an example. If I wanted the service times to be constant, then it's sort of intuitively obvious that this instruction should just be replaced by x equals the constant value, which would be 2.4. That would give me constant service times whose length is 2.4. If I wanted my inter-arrival times to be constant with average time of 0.25, then I'd write IA equals 0.25. Now, this actually comes out of the inverse transform method, because here's the distribution function. You can see that if I took a random number which lies between 0 and 1, put it on the vertical axis, and project it over to the curve, it's always going to hit the curve at the discontinuity and project down to C. So I'm always going to get the same value. So in fact, this is the inverse transform method for a random variable that is a constant. Okay, so in the homework problem, it asks you to do this for 4 cases. One where we have exponential inter-arrival times, exponential service times. Exponential inter-arrival times, constant service times. Constant, exponential, constant, constant. So there are 4 combinations. Okay? So now you can run the simulation. Of course, you still don't know what the answers mean, but you could now run it. Any questions about this? You can see how powerful this is. It's amazing what you can do with just a small amount of analysis here. Okay, so now my objective here is to do 2 things. One is I want to explore the Erlang loss system, and the other is I want to show why rate up equals rate down. Why the equations that are related, the rate up from each state to the rate down from the state above it, why that made sense. Because, well, let me go back to what our amazing theorem is, what we're supposed to show here. Okay, so I'm going to take this, I'm going to write this thing on the board again. Okay, first of all, there are 4 cases. So here's case number 1. Now, let me sort of work backwards here. Here's case number 2. So let me worry about those first. The last column says, calculate the Erlang B value. So this last column is the theory. This is supposed to be the probability of blocking. And we said that by the amazing theorem, no, we said that, well, by another amazing theorem. There are really 2 amazing theorems here. By the pasta theorem, we said that if we have Poisson arrivals, then the Erlang B value will give you a number that is in principle equal to two different measurements, which should in the long run produce the same thing. One is the fraction of calls that find the system in the blocking state and are therefore lost, and the other is the fraction of time that all the servers are busy. And those things are measured completely differently, and the simulation measures them differently. So the first question is, okay, let's calculate what this value is. So this is a calculation. Do it from the Erlang B formula. I'll show you how to do that, by the way, in a way better than just using the formula directly. Do it recursively. But in any event, that's some theory. So you can calculate that. Okay, now over here, it asks you to calculate what's called AB over A, which in the simulation is AB is the total time that all trunks are busy, and A is the total time that you have simulated. So this is the fraction of time that you're in the blocking state. Now, over here is K over NC, where K is the number of calls that overflow, and NC was the total number of calls that were offered. So by pasta, this and this should be equal, and they should be equal to that. In other words, this is the single theoretical value. And the theory says that whatever that value is, if I measure the fraction of time I'm in the state that is the probability of, or if I measure the fraction of customers who arrive when I'm in that state, then even though I'm measuring different things, if I simulated long enough, if I went to infinity, then this number and this number should converge to the same value, and the value they should converge to is this. Okay, so you can check that by computing this using the Erlang B formula, and then running the simulation. And in case number 1, you have exponential interarrival times, which means that you have a Poisson process, which means that this and this are going to should be the same by the pasta theorem. Okay, now let's look at number 2. In case number 2, you have Poisson input but constant service times. So we had a theorem that says, this was the amazing theorem. The amazing theorem says that the Erlang B formula is going to work as long as I have Poisson input, and it doesn't make any difference whether I have exponential service times or not. So now I'm going to run the same simulation, but instead of using this instruction right here, I'm going to use this one. And I have constant service times. So of course I'm going to get different numbers, but according to my theory, whatever they are, this Erlang B formula should describe both cases. Furthermore, because of pasta, since I have Poisson input, what's in this column and what's in this column should be the same. So therefore, it should be true that this number, this number, this number, this number, that they all should be approximately the same, and they should be, in theory, exactly that number. Okay, but now suppose you're in case number 3. For case number 3, according to this, you have constant interarrival times. Well, now our Erlang B formula doesn't apply. The Erlang B formula applies only if I have Poisson input. So that means I put an X here. It doesn't make any difference what the formula gives you. It's irrelevant. Nevertheless, now let's see. Okay, so it's irrelevant. So I should now be able to calculate this quantity right here, and I should be able to calculate this quantity, but there's no reason why they should be the same thing because they don't have Poisson input. Now they could be because the theorem doesn't say that, that the values will be different if you don't have Poisson input, but ordinarily they are. All right, so you'll see when you make the calculation that this number and this number are different, and neither of them have anything to do with that number. And similarly over here. In this case, once again, the Erlang B is irrelevant because here I have In fact, this case is the strangest case. This case is the most informative one because here's one where the inter-arrival times are constant and the service times are constant. So in fact, there's no variability. And again, what will happen is you'll get a value here and a value here. And these values won't have anything to do with each other. And they'll have nothing to do with that value, which is irrelevant. Now, there are some other things here, and what these boxes show you is, the way this is drawn is that everything that's within a circle is supposed to be the same number in principle. So when you run the simulation, you'll see that, although I still have some more explaining to do. Okay, so you're going to get things like this. So these things will be equal, but they're not necessarily the same as these things, and they're not necessarily the same as this. So this is going to illustrate the relationship between what the theory predicts and what the simulation gives. And the theory says that the simulation should agree with these things. There are two things that are important here. One is, if we have Poisson arrivals, then that and that should be the same because that's the pi j and that's the pj. That's the pasta theorem, which we haven't proved, but this is going to verify it. And the other theorem says that as long as we have Poisson input, then the service times don't matter. And so for the two cases with Poisson input, then everything in this row and everything in that row should be the same. Okay? Okay, so now you can run the simulation and see whether what I'm saying is true. But we still have a little bit more to do to understand that. In particular, I haven't really told you how to calculate this, and I haven't told you what this thing is over here. And furthermore, I haven't really explained very much about pasta, and I haven't explained why it is these theorems work, or why you should be surprised that they work. Okay, any questions at this point? All right, so I'm on page 77. Now I'm going to shift gears for a minute. And I want to talk about the pasta theorem. I want to talk about the viewpoint of the arriving customers. So I'm going to look at equation 2.2, page 77. Now, I'm going to define n of t. Here's my state diagram. Here is the number of customers present at time t. And so we might start out in state 0, then somebody arrives, somebody else arrives. Get a diagram that looks like that. Now, what I want to calculate is pi j of t, which by definition is this. This is going to be the conditional probability that the system is in state j at time t if I know that t is an arrival point. Now, we already have pj of t. There's two probabilities. Pj of t is equal to the probability that the number at time t is equal to j. It's the definition. Pi j of t is the probability the number at time t is equal to j given a condition, namely that t is an arrival time, or actually that t is just in front of an arrival time. That is, imagine that here is time t, and here is time t plus h, and we want the probability the system at time t is in state j if we know that an arrival is going to occur between t and t plus h as h goes to 0. So we're going to squeeze that arrival so it's occurring just after time t. So pi j of t is going to be this. It's going to be the conditional probability that the number at time t is equal to j, given, and this notation I'm writing down is defined in the book, given that a customer arrives between t and t plus h. in the limit as h goes to 0. Okay, so you wouldn't expect these things to be equal because this one is an unconditional probability and this one is a conditional probability given that I know that just after time t an arrival is going to occur. Or in fact, that just at time t an arrival occurs because I'm going to let h go to 0. So what I'm going to calculate is the probability that at the instant an arrival occurs, the number that was there just before it arrived was exactly j. So this is what the outside observer sees. This is the fraction of time that the system is in state j. This is what the arriving customer sees, because it's the fraction of time the system is in state j if the measurement is taken exactly when an arrival occurs, as opposed to averaged over all time. So you would not expect these things to be equal. And in fact, in general, they're not equal. But according to Pasta, they are equal. OK, now, the proof, or a proof, is in the book. But that proof is not rigorous. In fact, the first rigorous proof of this is Pasta. I believe it was 1982 or so, by Wolf. So the first mathematical proof was fairly recent. And in fact, it's not even in the book, not mentioned in the book, because the book was published in 1981. And although people knew this from the early 1900s, they knew it from Erlang's time, but nobody seemed to accept any of the proofs as being rigorous until Wolf's proof. And Wolf coined this word Pasta, which stands for Poisson arrivals C time averages. And what that means is that if Poisson arrivals then pi j of t, that is what's seen by the arriving customers, is equal to pj of t, what's seen by the outside observers. Now, our simulation is going to test that because we're going to run some cases where the inter-arrival times are IID exponential. And in those cases, they should be true. Then we'll run it in cases in which the inter-arrival times are constant, which is certainly not exponential. And in those cases, it'll turn out not to be true. OK, and I want to explain this. I think I can explain it in a way that makes sense so that you don't really need all the mathematics, in a sense. Although it constantly amazes me that I constantly go back and forth between thinking it's obvious and thinking it's impossible. OK, so where we stand now is read section 3.2, which starts on page 77. And then I'll talk about that next time. And next time what I want to do then is discuss this and then go through the Erlang B model so that the simulation makes more sense. And then talk about the Erlang C model, which is the one in which the block calls wait in a queue rather than are cleared from the system. And then the assignment that I'll give you when I get it worked out is to upgrade the simulation so that it works for the Erlang C system where the block calls wait in a queue. It's not that hard. I'll give it to you, actually. And then run basically the same simulation, the same calculations, and show what the relationship is between the formula and the actual measurements. OK, does anybody have any questions at this stage? Is it true that everything is making sense? If you don't think so, and you don't want to say so, you can write me an anonymous note telling me what doesn't make sense, and I'll be happy to discuss it. OK, so I'm going under the assumption that we're making progress here. All right, I guess I'll see when we do the first homework. All right, so if there are no questions, then I'll see you all on Wednesday. which is the general Erlang delay model, but I also like to specialize them for the case of MM1, one server. Because if you take some of the courses on local area networks and computer networks and stuff like that, everybody talks about MM1 and they derive MM1 separately. I want to show that you've already done all that, and MM1 is just a special case when s equals 1, and you'll see we'll get nice simple formulas for things like average queue length, average response time, average number in system, and so forth. Average time in system, average waiting times, all of those things. Simple results for MM1. Okay, any questions about this? Okay, so see you next time.